All right, good day, everyone. So we're going to be looking at a steam plant question here now, number 4. And it says here that we have a steam boiler plant, and it consists of an economizer, an evaporator, and a superheater. Okay, so at this point, we have to be very sure about what these devices are. Okay, the economizer, the evaporator, and the superheater. And we know what these are by studying the line diagram, okay, of a boiler plant. Okay, so this is very critical. And in this case, so they tell us that there's an economizer, all right, so that's to heat up the water before it enters the boiler, so we can have it run more efficiently. Then we have the boiler itself, which is also called the evaporator. Now, please be sure with those two names, evaporator and boiler, it's the same thing. And then we have the superheater up here. All right. And remember, these two devices, the superheater and the economizer, they reclaiming heat that comes out of the combustion chamber. Okay. If these weren't here, it would go and follow all the way along the ducting and out of the chimney, and it would be lost in the atmosphere and wasted. So what we do is we install the superheater and the economizer to reclaim some of that heat. And in this particular question, you can see I've crossed out the air preheater because they don't say anything about it. So we don't have that in this plant, in this particular plant. All right. And then they tell us that the pressure of the steam, okay, that leaves this plant, they tell us about it, and they say that it's 2 megapascals. So the steam that leaves the superheater is leaving the superheater at 2 megapascals, which is also 2000 kPa, and the temperature of that steam is 300 degrees centigrade. Okay, so when you get experience, you'll be able to quickly see that that is superheated. Okay, and you can see it's after the superheater. I've put it there, right? But how do you know that for sure? So in the boiler, it's also 2000 kPa, right? And the superheater isn't there to raise the pressure, it's there to raise the temperature, all right? So if you look at this, let me see the steam summary here that I made of this TH diagram, temperature enthalpy. At this point here, okay, so from 0 degrees up and up and up to this point here, where the latent heat section starts, the temperature can rise, all right? So remember, that's called sensible heat. You can actually feel the change in temperature. You can sense it, okay? And when it reaches the latent heat section, the temperature doesn't rise anymore, okay? So at this point here, along here, if we know what this temperature is, which is called TS for the saturation point, okay, where it starts boiling, if we know what that temperature is, then we can check, okay, what temperature did they give us? They said, okay, it's 300 degrees. So if it's anything higher than the saturation point, you know that if it's higher, then it has to be in the superheated region. You see there where the temperature starts rising again. Okay, so you put more energy in, more energy in, more energy in, more energy in. There's no rise in temperature during the latent heat section. But after a while, once it all turns into gas, the temperature can start rising again. And that's why sensible heating happens again after it's all turned into 100% steam. Okay, so let's look what TS is. So we can find what TS is. We go onto the steam tables, and we look on the properties of water and steam. All right. So let's check what TS should be first. Okay, so over here, you can see here, I go down to 2000 kPa, there, 2000 kPa, and let me get a highlighter here, okay, and I'm going to highlight this section here, so 2000 kPa, all right, now let's see, TS, if I go to the TS column over here, for the temperature, for the saturation temperature, you can see that the temperature is 212.4, all right, and obviously, any temperature higher than that at 2000 kPa is going to be superheated. So now we know, because our steam is 300 degrees, we know that our steam is sitting in this superheated region here, because the temperature over here is 212,4. All right, so we know that now. So the saturation temperature in the boiler is, so TS is going to be 212,4 degrees C. Okay, so I'm just writing that there so you can see. That's the temperature there, and that's when it's at superheated. Anything higher than that. All right. Okay, so let's go back to the question now and see what else they give us. So they say to us that the feed water enters the economizer at 36,2 degrees. Okay, so we can fill that in. So over here, you can see here at the economizer above the feed pump. So maybe it's coming out of the hot well, maybe it's coming out of the municipal supply, but they tell us here that this first temperature over here, T1, is 36,2 degrees C. Okay, and then at T2, it leaves the economizer, they tell us, at 86 degrees C. Okay, so there we go. They tell us that. All right. Then let's see what's next. Then it says the steam leaves the evaporator, and when it's leaving the evaporator, the steam quality is 0,89 dry. Okay, so the dryness factor, or the dryness fraction, is over here, let me see, 0,89. Okay, so that's what it's leaving the boiler at. Okay, so it means that the water is not completely turned into steam or into gas. 89% of that water has turned into pure steam, and the other 11% is still water droplets, right? So that's what that means there. Okay, and obviously the superheater, when it passes through the superheater, you see through the superheater here, goes through there. The superheater adds more heat, raising the temperature higher to 300 degrees, and it takes all those little water droplets and turns it into complete 100% gas, superheated gas, so that it can go through either the engine or the turbine. Okay, so that's that. All right, then they tell us that the plant uses 13,5 kilograms of coal per minute. Okay, so that's per minute, and the calorific value of the coal is 36 megajoules per kilogram. Okay, so every kilogram of coal that you use, it's gonna give us, when we burn it, 36 megajoules. Okay, of heat. And what else did they tell us? Okay, they tell us there that the steam is generated at a rate of 9,600 kilograms per hour. Okay, so the steam that is generated, it's coming at 9,600 kilograms of steam per hour. Okay, so that is our mass of steam. Okay, see that? MS, mass of steam. Okay, that's coming out of there. And they say the fuel is 13,5 kilograms per minute. Okay, so what we're going to do is we're going to convert that that coal, because we get in the steam per hour, we're going to also convert that coal per hour. And all we do for that is, because it's per minute, we're just going to times it by 60. So let's do that. We're going to say 13,5 times 60, and we're going to get 810 kilograms of coal. Okay, so every hour we're going to use up 810 kilograms of coal per hour. All right. So, and this is what we're going to call our MF, or mass of fuel. Okay, MF. So our MS is 9,600 kilograms per hour, and our MF is 810 kilograms per hour. All right. I think that is all the information that they give us. All right. So now they just want us, very easy calculations. They want us to calculate the heat transfer in the economizer. So they want to know, so this coal is burning here, right? And obviously there's when it's burning, it's putting heat into the water. okay? And not all of that heat can go into the water. You wish it could. We wish it could, but can't all go in there. Some of it comes out of the flue, okay, through the flue. So that goes up out, and it's going to leave the chimney, but not all. What we do is we recover some of it, okay? So it goes through, and then it gets to the economizer, and then it transfers some of that heat, which would have been lost, into the water, okay? So now they want to know how much of that heat, okay, goes into the water before it gets into the boiler, okay? And remember, all the heat, you must be very clear with this, all right? All the heat comes from that coal, okay? From the coal that's coming in, that coal with a CV of 36 megajoules, all the heat comes from that. So the heat that's going from the economizer to the water is also coming from that coal, because remember, it burnt up and went through the flue. Okay, so let's see. How are we going to calculate this? Okay, let me just get something here to write on. So first of all, they tell us, so you can see here, the temperature is changing, or it's increasing before the economizer from 36.2 degrees to 86. All right, so that's what the raise in temperature is through the economizer. So what we can do is we can find out how much enthalpy how much the enthalpy has increased, or how much how much heat has been applied when it goes through the economizer. All right, so let's do that. So remember, on the economizer here, on the TH diagram, you can see over here, this section here is the economizer, right? And the temperature, they say in the beginning of the economizer, is 36.2 degrees C, right? And then after it leaves the economizer, you can see over here, the temperature now is 86 degrees. Okay, so you can see there's been a rise in temperature. And we can also, on this diagram here, we can put here the saturation temperature, TS, which is 212, what was it, 212.4. Okay, so we can see that temperature as well. Okay, so this point here, if we go down here, this point here is our first enthalpy. That's enthalpy 1. Okay, and the next point here at T2 at 86 degrees, that's H2. All right, so we want to know how much has, so it started off at 36.2, which is over there, and then it increased to H2, which is at 86 degrees. Okay, so let's fill that in on the diagram as well, so we can see that. So obviously, at T1, that's H. We want to know what the H1 is there. All right, so what is that? And at T2, we want to know what the H2 is. Okay, so we get that from the steam tables very easily. So we're going to go, first of all, what's the first temperature? It's 36.2 degrees. So you go to the steam table and find that. Okay, so here you can see right in the beginning of the steam table, on the first page, you go to 36.2, and there we have it. Okay, so you can just put a line there, and you can see there. So there's the first temperature, and we have to read off the enthalpy value. Now, if you look at the top here, we have HF, HFG, and HG. Now you must ask yourself, what is the phase of the steam, okay, or the water, okay, that's at that part of the plant, okay? So over here, after the feed pump, is it water? Is it pure water? Is it water and steam, or is it pure gas? Okay, pure steam. And obviously, because we pump in water from the hot well, it's obviously just water, because you're not going to be pumping steam. Okay. So what are we going to read from? Which column? So we know it's water, so we're going to read from the HF column, okay? Because H, it stands for enthalpy fluid, okay? So that's how I remember it, okay? Enthalpy fluid. So we're going to read that value off, and the value is 152. Okay, so that's the enthalpy value. Okay, again on our TH diagram, you can see over here, the TH diagram here, you can see H1, and that's going to be what? It's going to be 152 kilojoules per kilogram. Okay, so there's our H1. And our H2, we're going to do the same thing. Okay, so let's go. So H2, remember that's after the economizer at 86 degrees. So we're going to go down on our steam tables now, further down, and we're going to go to 86 degrees. Okay, let me get that in camera, 86 degrees. Okay, and pull a line underneath that too. Okay, and again, which column? Is it HF, HFG, or HG? And obviously, it's still water because it hasn't entered the boiler yet. So we're going to read off the HF value, and HF is 360 kilojoules per kilogram. Okay, so we're going to say here our H2 is 360 kilojoules per kilogram. Okay, and then on our TH diagram, we're going to fill that in as well. So that's 360 kilojoules per kilogram. Okay, so you can see there. So as the water went through the economizer, the heat that was applied to that water went from 152 to 360. Okay, so how do we calculate it now? Because obviously, if you look at the value of enthalpy, it's kilojoules, so heat energy per kilogram. Okay, and we know that we didn't send 1 kilogram of water through, we sent more than that. Okay, so this is the formula to calculate it now. Okay, so we're going to write here for the economizer, we're going to write H economizer, see there, enthalpy through the economizer, and we're going to write MS, which is the mass of the steam over the mass of the fuel. Okay, and we're going to open brackets, and we're going to say H2 minus H1, because remember the enthalpy increased, and you want to know how much it increased by. I think that was 152 kilojoules per kilogram. Kilojoules per kilogram. Okay, how much it increased by? Because remember, this initial temperature when it's at 36.2 degrees, that didn't come from the steam. Okay, yeah, so that didn't come from the steam of or from the heat of the coal. Okay, so here's the formula, and all we do is we're going to write now firstly the mass of the steam, which is 9,600 kilograms of steam per hour, and we're going to say how much fuel did we use in that hour, and remember it is 810 kilograms. Okay, and then we're going to write 360 for H2 minus 152 for H1, and then we're going to calculate that answer. And before I calculate that answer, I just want to show you here now. So how much steam went through, okay, for that kilogram for 1 kilogram of coal. So if we say 9,600 divided by 810, we get 11,85. Okay, so 11,85 kilograms of steam was generated. Okay, was generated for 1 kilogram of coal burnt. Okay, so now we're going to say that, and then the answer comes out to be 2,465,185 kilojoules per kilogram of fuel. Okay, so what does that mean? We have to break this down now. So it means that for every kilogram of coal that is burnt, okay, we're not going to look at the 810 kilograms per hour. We're just looking at 1 kilogram of coal. Okay, when that 1 kilogram of coal is burnt, the portion that gives heat through the economizer to the water is this here. Okay, so that's how much heat the water gets through the economizer from 1 kilogram of coal. Okay, so that's what that means. All right. Then what do they ask next? Next, they ask for the heat through the evaporator. Okay, through the boiler. Okay, and now it gets a bit easier. So through the evaporator, so after the evaporator, before the superheater, we're going to call this H3. Okay, H3. So we've got H1, H2, H3. Okay, so how would we find out how much heat went from the fuel to the evaporator, or to the water in the evaporator? So it's the same formula again. Okay, so again, we're going to write here this time, we're going to write H evaporator, I should say, evaporator, H evaporator, and that is going to be the mass of the steam over the mass of the fuel. Okay, H3 minus H2. Okay, so if we just look on this TH diagram again, you can see here, so there's H2, okay, and there it enters the boiler at that point. All right, and they told us that when it leaves the boiler, the steam is over here, okay, and they said the steam quality is 0.89. Okay, so it's not all the way to the dry point, eh? So you must remember that it's not all the way to the dry point. So our H3 is over here, H3. But how much? What is this value? Okay, so obviously we can't read that value off the steam table, so we have to work out what it is. So how do we do that? So H3 equals HF. Okay, and why HF? Because this portion over here is the fluid. Okay, that's HF, there's the fluid, because we need to go from this point to that point here. Okay, so that's the fluid part. And then the steam tables tell us what HFG is, okay? And that is this portion here. HFG, okay? But we need to go not all the way. We have to go 89% of the way, okay? So how are we going to figure that out? So it's very easy. So the formula is to calculate what H3 is. It is HF, so the fluid there, plus X for the dryness fraction, times HFG. So we can find out how we're going to get 89% of the way there. All right. And these two values we can read off the steam tables. So H3 equals, let's go to the steam tables. So now again, we're not going to the superheater tables because it's not dry yet. So we have to go to, again, 2000 kPa, and we read the first column, HF, okay? So we need to know when it's fluid. So that HF is 908, all right? And then we're going to say plus the dryness factor, which they gave us, 0.98, times, and this is HFG. So we go back to the steam tables at 2000 kPa, and instead of HF this time, we're going to read off HFG, which is 1889. Okay, so what is that on this on the TH diagram? It's this one here. So this over here is 1889. Okay, remember now, but we're not all the way there, so we have to multiply that by the dryness factor. So there we have it. There's the formula. H3 equals 908, which is HF, plus the dryness factor times HFG. And that will give us, let me see here what it'll give us. It'll give us 2,589.21 kilojoules per kilogram. Okay, and you can see that value there is just less than HFG, okay, or HG, I should say, HG, when it's a complete gas, which is 2,797. So that would be over here, 2,797. But we over here. Okay, so our value there is 2,589.21 kilojoules per kilogram. All right, so now we have that. Okay, so now we have the enthalpy of when it leaves the boiler. So now we can find out how much enthalpy was given to the water just in the evaporator section. So remember, if you look here now, this portion here was the economizer, how much energy the economizer gave it. So that's H2 minus H1. For the boiler or the evaporator, it's from H2 to H3. So how do we know what that is? It's H3 minus H2. So this section here is what the boiler gave the water. Okay. So we go back to the formula here, and we're going to say again 9,600 over 810. I'm not going to do that. That is again 11,85. And then we're going to write here H3 now is 2,589,21 minus H2 is, like we said last time, 360. Okay. And then we're going to calculate that, and that will give us 26,420,267 kilojoules per kilogram. Okay, and you can see it's a big number. Okay, the economizer only gave it 2,465, but the evaporator is giving it 26,420 kilojoules per kilogram. Okay, and why is that? Because the boiler is the main the main device that's giving the energy over to the water. Okay, so this is our main machine. Okay, so now again, they want us to tell them how much energy now did the superheater give the steam. Okay, so if this is H3, this point here where it comes out of the superheater will be H4. Okay, and how are we going to calculate what H4 is? We've got H3 now. We need to calculate what H4 is. And on the TH diagram, it's going to be over here. So H4 will be there after the superheater, H4. Okay, and this is also, we don't have to calculate this because we have our steam tables. And this time, we're not going to the water and steam properties. We're going to the superheated properties at the end. Okay, so we go to the superheated table, and we're going to read off. So we're going to go, what is the pressure going to be? It's still 2,000 kPa. You see there? Still 2,000 kPa, but the temperature is 300 degrees. Okay, so we go down to 2,000 kPa over here. So we go there, and we're going to go across because the temperatures are on the top here. Okay, and our temperature is 300 degrees. Okay, see that? And our pressure on the side here is 2,000 kPa. And then this middle one tells us here that the enthalpy is 3,025. So you see there, and there. And then you can get that value there for H superheated. That's why it says HSU for H super. Okay. So very easy now. Now what we're going to do is we're going to write out the formula again, H sup for H superheated. And that's going to be mass of steam, again, over the mass of the fuel. And that's going to be H4 minus H3, because that's after the boiler, that's after the superheater. And that's going to be 11,85. And we read that value now, just now, 3,025 minus, what does it come out of the evaporator at? Over here, H3 is 2,589,21. Okay, and then we can calculate that answer. let's see here. That's going to be 5,164,919 kilojoules per kilogram. Okay. All right. So let's see. We can put that on the TH diagram now. Okay. So let's write that down. It's going to be 3,025. Okay. So that's that value there, H4. All right. Now, how do we calculate the heat transfer in the superheater now? Okay, how much heat was gone into the superheater? So it's H4 minus H3. Okay, so you see how easy it becomes. H4 minus H3 is the superheater, and that's how we just subtract the two, and we get what the heat transfer in the superheater is. H3 minus H2, this section here is the boiler section. H3 minus H2. H2 minus H1 is the economizer section. All right, and that's that. So they ask us for two more things. Okay, let's just do the efficiency. Okay, the efficiency. So efficiency. Okay, we got efficiency of the boiler plant. Okay. So that's the whole plant, eh? That's the economizer, the evaporator, and the superheater. And that equals to the mass of the steam over the mass of the fuel, and how much energy went from how much energy went to the steam. Okay, how do we know what that is? How much energy went to the steam? And that's obviously H1, H4 minus H1, and that would tell you how much energy went to the steam. Okay, so we're going to write there, open bracket, H4 minus H1. And remember, we didn't get that from the coal, H1. That's what it was given to us as. Remember, it entered before the economizer at 36.2 degrees. Okay, so that's what we gave to the water. And what did we get from the coal in total? It was the CV value, eh? Okay, so that's what the efficiency is, and we times that by 100, and then we get it in a percentage. Okay, so that's going to be, in the end, it's going to be 9,600 over 8,100, which we know is 11,85. Open bracket, 3,025 minus 152. So that's our H4, H1 over the 36 megajoules from the coal. So we're going to say 36 times 10 to the 3. Okay, why to the 3? Because those are in kilojoules, kilograms. So we say 36 times 10 to the 3 times 100, and we get the efficiency. All right. So I hope that helps. Yeah, I hope that helps.